As we start working with more quadratics and other polynomials that are raised to an even power, we will end up with square roots with negative numbers, which produce imaginary or complex numbers. You may recall looking at like a quadratic formula where we have the square root and you end up with a negative value underneath the square root. Again, this is how we get imaginary numbers, so we're going to look at how to simplify that real quick. This can be rewritten as the square root of -1 times 27. It's not necessary to write it like that, but in writing it like that, we see what we define to be I. I is defined to be the square root of -1. So if I separate -1 and 27, there is a property of square roots that allows me to separate values that are multiplied underneath a radical into two separate radicals themselves. So I could rewrite this as the square root of -1 times the square root of 27. Again, all of that is not necessary. I'm just using it to show you how this simplifies out. So now that I have them separated, I see that the square root of -1 is just I, and I can go about simplifying the square root of 27 as seen in previous videos. 27's prime factorization is 3 times 3 times 3. Since this is a square root, or the second root, I do need pairs of 2 or groups of 2 to be able to pull it out of the square root. A pair of 3's comes out as 3, and the lone 3 stays underneath the radical. This looks kind of funky. Generally, you're going to see it written 3i square root of 3. There are some books and other websites and things that will put the I after the square root. It's not wrong by any means. I know whenever I start writing things out, I'm not quite as neat as I should be, and it can look like my I is underneath the radical. I should not be underneath the radical. It should be outside the radical, so I like to keep it up front. Long story short, I put it in the front. You can put it in the back if you want to. Just be sure that it is not underneath the radical, it is outside the radical. Alright, so there we go. That is the long drawn-out way of simplifying square root with a negative argument. So let's look at a couple of operations. Let's say that I have the square root of -120 over the square root of -10. So I'm trying to divide these two square roots. We have a property just like with multiplication where I can combine the two arguments together. Same thing for division. These are being divided, so I can put them underneath the same radical. When we're dealing with imaginary numbers, though, we want to write them in terms of I first, because we're not exactly sure how the I's are going to interact, and I'll show you what I mean by that in just a second. So I'm going to write these in terms of I. Since this is negative, I can go through the long process or just know that the negative comes out as an I. And same thing in the bottom. So I get I square root of 120 over I square root of 10. I divided by I, just like any other value, cancels out. So I get the square root of 120 over the square root of 10. Now I can use that property. Like I said, if I have two radicals multiplied together, I can multiply their arguments and put them back into a single radical. And the same thing works for division. If I have two radicals being divided, I can them into one single radical. So I could rewrite this with the fraction on the inside, 120 over 10. Now this is pretty simple. 120 divided by 10, that simplifies to the square root of 12. 120 divided by 10 is 12. And now this is a much simpler square root to simplify. The prime factorization of 12 is 2 times 2 times 3. I have a pair of 2's, so those 2's will come out, and the 3 stays in. So there is the quotient of those two radicals. Let me do one real quick with multiplication. So let's say I have the square root of -64 times the square root of -49. And I want to simplify these. So again, we have the property that says if I have two radicals that are being multiplied together, I can simply put their arguments multiplied together under a single radical. But we need to write them in terms of I first, In the last example, the i's canceled out, but that won't necessarily always be true. So I'm going to rewrite these. Negative 64, I'm going to pull the I out. So this would be I square root of 64 times I square root of 49. Now, there's a long way to do this, and there's a short way to do this. I know the square root of 64 is 8, and the square root of 49 is 7, so I'm going to go ahead and simplify those. That's going to be the shorter way. The longer way is to use the property to actually multiply, you can't see that, to actually multiply the arguments together and put them back under a single square root. I don't want to multiply 64 times 49 and then try to find the prime factorization to simplify that. That's just too much. So I'm going to go ahead and simplify these. The square root of 64 is 8, so this gives me 8i. And the square root of 49 is 7, so this gives me 7i. And now I'll multiply. The I is going to work very much so like any other variable. So if I multiplied x times x, I would get x squared. If I multiply I times I will get I squared. So 8 times 7 is 56, and I times I is I squared. Now, what do I do with the I squared? Let's come back up here to what the definition of I is, square root of negative 1. Now, if I square both sides, I get what I squared is. If I square a square root, these are inverses, we'll talk about those later, but they are inverses and they cancel out, so I'm left with just negative 1. So I squared simplifies to negative 1. So I can simplify this down here. 56 times I squared is really just 56 times negative 1, which is negative 56. Now, jump back here real quick. If I had started off just by multiplying the two arguments together, then I would have gotten a positive number and I would have lost that negative. So it's very important that we write the values in terms of I first and go from there, because you never know what the I is going to end up doing.